Okay, welcome back, everybody. I probably said this like 20 times. MCMC is my favorite topic. So it's my favorite thing out there. It's my favorite set of algorithms. I have favorite algorithms and I have favorite theorems. And they all stem from this stuff. So mostly we're going to focus on practical issues, the algorithm, how to use it, and we'll go theory light, but I'll try to give you at least glimpses of what the theory is. And I think I'll try to explain it in a fairly intuitive manner, you know, what the conditions are without getting overly technical, because I'm not going to test you on all that stuff. But if you ever take a stochastic process class, they'll fill in the gaps in a way that's not MCMC, but it's kind of the way that a mathematician might study Markov chains. The way that a statistician uses it for Markov chain Monte Carlo is actually the opposite. And I'll try to address those two comments. I sometimes teach an MCMC class, and I like to go into all the theoretical details there. We spend a lot of time on that stuff. But at the end of the day, I think it's all about the project. You know, how do you use this stuff? How do you use it to overcome computational challenges, problems that you know, models that you want to sample from and understand, but you can't work out all the math. So it's just too much, and possibly the math is impossible to work out in closed form. So, and that seems to be the experience that I have with anything outside of just standard regression models. You know, so I do think that regression models are pretty useful, but a lot of times I start with that and I start changing aspects of the regression model. Maybe the tail behavior or how the variance varies in different parts of the space, things like that. So that whole like football shaped thing data, I never really see that in reality. So I have to tailor those ideas, add components, mixture models, things like that to standard regression models. And then I can kind of build that up, the model, and then how do I work out what the actual inference is? I use Markov chain Monte Carlo. So we'll kind of see that in terms of our example today. We've looked at this example. So we'll get here at some point where you might want a joint inference on mu and phi given some data, and your model might look like this. So phi to the n over 2, e to the minus, and I'll put a -1 in there. You probably know where that comes from, probably my prior. So e to the minus phi over 2 sum of the xi's minus mu squared. And we've looked at this distribution before. So this is the joint distribution for mu and phi, and there's a few assumptions. One assumption is the data came from this model. Just to remind us what phi is, it's 1 over the variance. So everything is IID, and I used a certain set of priors to do this. So I like to write it down like this these days, that my joint prior, which is really just a product of two priors. So a priori, everything is independent. I don't have good reason right now to inject information about their joint relationship. I'm not sure what it is. And so this is just our typical prior that we've been working with. So limits of conjugate priors have good properties. We've liked the properties of using this prior in doing forecasting, for doing inference. So we'll understand it jointly after we can finally understand what is this distribution right here. So we might not understand what it looks like, but we know that there's a joint relationship in phi and mu, because this phi is always going to be tangled up with that mu. So they have something to do with the data as well. And so you'll never be able to factorize those apart. You can try, so, and you will never get it. So these don't factorize, so there's some joint information in here. And we might want to understand what that joint is. So that's an example we'll study. You might call this the normal gamma distribution, and that happens for fairly obvious reasons. Somebody help me out. What is this? So this is just the integral of the joint d phi. So this is the marginal distribution. We might understand what this distribution is. We derived it. Somebody help me out. What is this? No. T. This one's T. So if you do the integral, this is going to look like a gamma. So when you do, this is going to be the kernel of a gamma. Looks like that in terms of phi. So when you integrate it, it's going to be the inverse normalizing constant of a gamma, which looks like a T after you do some algebra. So this is a T. With some degrees of freedom, nu. There's some location parameter and there's some scale. So I'll just write it down this way, location, scale, and you've worked this out before. And so this is what? N minus 1. What's this? X bar. What's this?
1. Is it S squared over
S squared over,
just over N.
over N. So the N minus 1 is built into S squared. So, and square root if you want to just speak the same language that other people speak. I usually square the thing and still call it scale. So that's the scale parameter. So we've done a problem. This one we can work out as well. So this is some gamma. This has something to do with S squared as well. It's N minus 1 over 2, N minus 1 S squared divided by 2. Those are the two parameters. So N minus 1 over 2, S squared, N minus 1 over 2. Expectation of this thing is 1 over S squared. Kind of makes sense. So everybody know this from a previous exercise? Where did you learn this?
Homework.
Homework. Yeah, this is like homework 2, right? So we know these, we worked at these. We also know some other things. I want to just tell you about these and remind us just real quickly. We knew this. So this one was a normal. Where was it centered? X bar. What was the variance on this thing? It's sigma squared over n, which is 1 over phi n. So just rewriting it a little bit differently. What was this one? This was some gamma. Does anybody remember what the parameters are here?
Is it just n over 2 and s squared n over 2? Or
N over 2.
and then s squared?
Would you use S squared? Because you get to know mu. What if we stared at this? Isn't it all right here?
Oh, yeah.
So if I looked at this thing, so that thing. So how do you do this? You write it down, you recognize real quickly. So this is going to be sum of the xi's minus mu squared over 2. So that looks good.
But we still need an n in the numerators of those.
So this one's alpha. This one right here is the beta term. So I think it's right. Make sure you code it up right, check your algebra, your code doesn't work. It's one thing is wrong. It could just be a very simple thing. So get used to double checking your work, triple checking it. So you'll find your error and be like, oh my goodness, I just assumed I wrote that down right. Normal stuff. Here, let me just tell you a fact. So here's a fact. So these kind of seemed a little bit contrived, what we've done before, what we've derived before. We were just kind of doing things intuitively, and I promised you these would eventually be useful to you. Let me give you some utility right now. So here's a fact, that if I want to sample samples from mu and phi, I can do this. So I'm just going to index everything by t, just my indexing iteration A lot of times I usually call it time, but I'm just thinking of some ordered set. So it's just my index. T goes from 1 to some large number, large. We'll discuss what large means soon. So if I end up sampling mu t from this distribution, pi mu, given phi t minus 1, I'm going to iterate this and build an iterative algorithm, so I need to initialize this thing. And so I need to set phi 0 in this algorithm. I need to initialize it to some value. So initialize. And x, I know how to do this sampling right here. It comes from a normal distribution where I plug in x bar. It's always going to be the same, and I plug this thing in. This is going to vary depending on the iterative step. So I'm going to take that phi and I'm going to replace it with some value right here. First time I come around sampling from this, I'm going to pick my initial value. After the second step right here, I'm going to update that value right here, where previously I updated mu. So I'm going to sample from this distribution, x, and mu t, where this is my current mu t that I just updated, and this one's going to come back around right here. So I've set up this iterative loop of sequentially sampling from these conditional distributions. I want to give them a new name. I think I've used this name before when we first discussed these. These are the full conditional distributions. So this is the full conditional distribution for mu. What do I mean by that? It's conditioned on everything else in the model. I didn't integrate anything out. I just wrote it down. So here's a fact. So eventually, samples mu t, phi t. So there's going to be, make this a little bit cleaner. These samples, give it some set notation, mu t, phi t. So what I mean by eventually is I'm not going to set this equal to t is equal to 1 right here. The samples on the first iteration might not be sampled correctly from the right thing. I haven't said what they're sampled from. Let me just tell you that these things will be sampled from the joint distribution. This distribution that we're trying to study. I'm telling you a lot right now. I'm just telling you facts. I haven't explained anything. I'm just writing something down. So what I've written down is something that is easily implementable. Sample from this, get a mu out of it, plug that mu in right here, sample from phi. I wrote this in this order. I could have changed the order that I did everything in. We notice we don't need an initializer on mu. So because our first iteration is conditional on phi gives us a mu, we could have reversed that, and it would make no recognizable difference in our algorithm. So the order of updates, I don't want to say this too strongly, makes no difference, but it should make no recognizable difference if you've coded up everything reasonably and everything is stable and blah, blah, blah. It can make a difference. So if it makes a big difference, you can randomize these steps and decide which one you want to do first, and it will converge to the same thing. So what I mean is that this eventually converges to something, and it converges to the joint distribution. And it kind of makes sense. So it's easy enough to do this. Sample the mu, sample the phi. I'm getting it from models that are proportional to the joint distribution, so it kind of makes sense that maybe eventually, what would the joint samples converge to? The joint distribution. What else would it be? I don't know. So I do know the proof for proving this, but we don't know the theory yet on what we're supposed to even prove in the first place. So let me just say this. These samples eventually converge. So I'm not going to set this at 1. I'm going to set this at some number bigger than 1. And I'm going to call this cap B. And that has a name. That's called the burn-in period. So So it's the number of iterations it takes until I eventually converge to the joint distribution. Here's another fact. Once I start sampling from the joint distribution, I don't leave it. So you start sampling from the joint distribution, you continue to sample from the joint distribution. That's nice. So when it converges, after it's converged, it stays converged. It doesn't jump out of convergence. And it converges in the strongest sense possible. So almost short convergence. So if you're ever writing any code and it looks like it's converged for a while, and then it stops converging, you have some theory, or at least a promise of some theory, that's a implementation error. So they're not supposed to do that. So probably some numerical error that's popping up in your sampler on some iteration and it throws it berserk for a while. So, does anybody know the name of this type of sampler?
Gibson?
This is a Gibbs sampling. This is called Gibbs sampling. I want to point out a couple things about this. This is a Markov chain. So just real quickly, what is a Markov chain? They told me this a long time ago. Has everybody heard of the term Markov chain? Does anybody not know what a Markov chain is? Good. What is it?
So you have some set of states,
Yes.
some finite number of states.
Could be infinite.
Yeah, it could be infinite, yeah. And for each state, you have a set of probabilities that will transition to any of the other states.
Oh.
You can represent that with a matrix, and
Oh.
you can see if it will converge to some probability that it will be in any given state after infinite time.
What is that called?
Some number.
Okay. Does anybody know what that's called? That there's some probability of being at any particular state in some amount of time? Nobody knows what that's called?
Steady state.
Steady state. Yeah, it kind of feels steady. That's not what they call it, but it is like a steady state. So it stays there. Goes through this process, this Markov process, and it stays in this steady state. There's a different name that people use, but I like that name. It seems to imply the same thing. So, anybody? Any math majors around here? Fixed point, no, that's a different thing. So I want to differentiate this between fixed point right here. This does not converge to a point, it converges to a distribution. So just like Newton's method or something like that, you're going to be iterating through and converging to some point, and you use fixed point theory to show what you converge to. So it converges to a point. This does not converge to a point, this converges to a distribution, so it always bounces around. Same concept, different math. Markov chains, what is that steady state called in a Markov chain? Jared?
I'm not sure. Sorry.
Jim? Francis? We're close. What did they teach you about Markov chains when you learned? They're just probabilities of transition? Conversation's over? You never did anything with them?
I mean, for me, it was actually in passing through hypotheses.
Okay, so you've heard people use this stuff. Yeah, okay. Cool, okay. Well, let me teach you something about Markov chains. That state is called a stationary distribution. So similar sort of thing, state. So steady state, stationary distribution. So it can also be called limiting distribution. So a Markov chain, so let me just tell you the Markov property real quickly. It means that if I have some probabilities of substate, I'll call it xt. So this is the state at time t xt. So I'm going to think of an ordered set of indices. So conditional on everything else, xt minus 1, where I started before, all the way back to the very beginning of the process. I'll call it 0, but if you want to index it 1, that's fine. This is the beginning of the process, the first state. So I just happen to have started my indexing at 0 up here. So I will maneuver that as many times and re-index at 1 or 0, depending on how I feel in that particular moment. So watch out for that. This thing right here is the probability of xt given xt minus 1. So the Markov property is that the transition to what xt at time t only depends on the pass through its immediate previous state. So it's conditionally independent of all other states. That doesn't mean it's independent of all other states. It means given xt minus 1, I don't need to know those previous states. So xt minus 1 depends on xt minus 2. So xt depends on xt minus 2, but given xt minus 1, I don't need to know what it is. I think of this like walking. So if I'm walking around, so I could probably do a pretty good prediction of where I'm going to go next, you know, just based off of where my foot is at, you know, with the previous thing. So, you know, I could, if all of a sudden I start to wiggle around and I catch a rock or something on my ankle, you could probably still tell me where I'm going to go. About the same place, probably. So if I were running, however, and I caught a rock, so where I'm going to land is going to have to do with a lot of steps. So you're going to see me stumble and start bouncing around and oh my goodness, and now I'm off the curb and on the ground. And it has to do with a lot of things. That's not a Markov process. So that walking or something like that might be Markov you might be thinking about. So a lot of processes can be modeled through Markov processes. You can extend these to hidden Markov processes, which are no longer Markov, but a layer of it is Markov. So if you wanted to do something that's not Markov, but use Markov chains and hierarchies of your model, you can do that and then do something that's not Markov, which is kind of cool, but conditionally on a certain set of states, it is Markov. So these are extremely valuable modeling tools in things like time series. So that's the Markov property. I want to point out that a Gibbs sampler is a Markov chain. So why? Because I only condition on the previous past, the step in the immediate predecessor, I should say. So at time t plus 1, what samples did I use? I used mu t and phi t, and it was only conditional on those states when I did the updating. So on the next sample around, I use the next phi t, and then I update the mu t, and I update that, and I get a new phi t. So I didn't use the t minus 2 indices at any point. So once I have new samples. So this is a Markov chain, and that's easy to see. So the theory that we want to study or Markov chains. So I will just point out that all Markov chains have stationary distributions. There's another type of distribution out there that's called a limiting distribution. Not all Markov chains have those. When limiting distributions exist, they're guaranteed to be the stationary distribution. I'm going to try to cover this theory in like a couple seconds, really, because I don't think it helps us a ton to implement the algorithm. So let's just get back to our presentation real quick. We were looking at this last time, and I kind of showed you the idea. What I want to do is sample from some target distribution, and I'm going to employ a Markov chain algorithm to walk around the space until it converges to sampling from this posterior distribution. So this is what we looked at last time. I'm going to have these Markov transitions. So I didn't tell you much about how these points are being generated. Truth is, I just drew it, you know, but it's an idea. But the idea is that once I have a point down in space where I transition to in the next point in time, the next iteration will be a Markov transition. So it'll only depend on the current state for updating. I do that, and eventually it's going to converge to something. So the idea of Markov chain Monte Carlo algorithms is that eventually this will converge to the target distribution and eventually produce samples. I never like to show good news first. This chain is not converged, but it's getting there. And so if the algorithm is developed properly, eventually this histogram will look like that curve that I'm drawing to represent some two-dimensional density. So here's the algorithm. And I'm going to write this down in terms of our Bayesian notation. Right now I've written it down with just any old arbitrary notation, so I'm going to rewrite this in a moment. But what we're going to do is we're going to propose a value, and then we're going to accept with some probability. So there's going to be a proposal, and then there's going to be an acceptance step. So two things are possible. So I can either move to my proposed location from my current state, or I can stay where I currently am. Those two things are going to happen. So if I stay in the current state, I'm going to hold on to the frequency and say, I've stayed here before. And I'm going to make note of that. And I'm going to keep those samples. And that's going to reflect that it's probably some high probability area that I don't want to transition out of so fast, so I can make that part of the curve higher.
So this part of the Metropolis-Hastings algorithm is what we're going to use to sample UT and VT?
No, this is a different algorithm.
The entire algorithm.
So this one's Gibbs sampling, and this one is called Metropolis-Hastings. I shouldn't say they're entirely different, because they have something to do with each other. So not all Metropolis-Hastings algorithms are Gibbs samplers, but all Gibbs samplers are types of Metropolis-Hastings algorithms. It's one of those rectangle square things. So I haven't gone into any details yet, I'm just throwing down some ideas so far. So it depends on how I set up the proposal structure. So the idea in this algorithm is I propose from some distribution. I've unfortunately called it Q. My target is P. We will change that again before the lecture is over, what the target is and what the proposal. Before I called them F and G, I think. So the target was F and the proposal is G, and I'm going to change that again. So you have to just get it into this idea. There's the target you want to sample from, and there's a proposal that you're able to sample from, just like an accept reject. So, but we might structure our proposals a little bit different using this algorithm. So I've got some proposal. The proposal is allowed to be Markovian. So it can't be anything other than a Markovian proposal. It could be an independent proposal, but it can't depend on two previous states for this to still be a Markov chain. So this is allowed to be a Markov proposal that I can look at my current state and update my proposed state. And then I decide whether or not I want to move to that new proposed state. So when I have some acceptance probability, so this is a number that we're going to use, and we're going to bound it by 1 so that it's a probability. I just want to point out what this number is. It's the ratio of our targets compared to the inverse ratio of our proposals. You might not see the invert in there, but that's what it is. So you can also think of that as the ratio of importance ratios. So, and I'll be more clear about that once we write it down on the chalkboard. So here's the algorithm. Metropolis-Hastings all has this in common. I propose, and then I decide whether I want to move to that proposed state or stay in the same location. What I'm going to do is I'm going to write all this stuff to memory, and I'm going to have some big file at the end of the day with all of my samples. And those samples will eventually converge to sampling from our target P. That's a promise if everything is implemented correctly. So we haven't given any theory. We've just said there's 2 steps: propose, accept. There's no reject or stay in the same location. So generate a big file and then chop off the stuff that hasn't converged. Nicely, that stuff is ordered properly for you. It's in the beginning set of iterations, not in the middle. I don't have to go searching for it. I just need to monitor whether or not this thing is converging to something. I have to be able to monitor and diagnose non-convergence as well. So it's just like any algorithm. So there's a number of different proposal strategies. So let's just stare at this real quickly. What's the proposal in Gibbs sampling? This is so brand new that I don't exactly expect you to get it.
The initiating value that we have?
The initial value is my proposal. That is the least random thing in the world. So that's just our initial value. That will be in common for all iterative algorithms. They initialize somewhere. So that's not the proposal, that's just where I start the chain. That will determine how fast I converge. If I start in the stationary distribution, I'll remain there. If I'm outside of the stationary distribution, way off in the tails of the distribution, it'll take me a while to get there. So it certainly affects the rate of convergence, and we'll study that. And that's what I'm going to do in my code. I'm actually going to hamper everything, where I'm going to vary Metropolis-Hastings steps on both of these. I'm going to pretend I don't know how to sample from them. So I'm going to do something kind of ridiculous to slow down convergence, but it'll converge to the right thing. So the name of the game in Markov Chain Monte Carlo land is to build algorithms and proposal strategies that converge quickly. We'll talk more about that later. The proposal's not really here. There's an acceptance with probability 1 going on here. I just accept, I don't make a decision. So it turns out, if I go and I plug in the full conditional distributions into this ratio, we won't do this on the chalkboard yet, but I think outlining that idea is probably an important idea, that if I use the full conditional distributions to propose, this number R is always the same number. Does anybody know what it is? I'll give you a hint. You always accept. It's 1. So it's guaranteed to always be 1. So it'd be a waste of time to do this evaluation. What I want to point out is Gibbs sampling is a type of Metropolis-Hastings sampling. And most importantly, this is easy to implement, at least in spirit. So I've got a ratio, I know how to write it down. It's the ratio of targets to the ratio of proposals. And the ratio of proposals is inverted. So what I mean by that is I have an X star upstairs, but this distribution is X star downstairs. So the X star is showing up in the opposite place. This is conditioning on a value. So what's random here, X star, what's random here, X star, what's random here, XT, and the other XT is down there. So they're flipped with respect to each other. I'll try to explain to you in a moment that that's intuitive. We should do that. There are a lot of different proposal strategies. I'll probably take a picture of this slide and post it to Slack if you want to see it. And this is basically all the research. So there's whole books. There's lots of books on different proposal strategies. Lots of math showing you properties of convergence, how fast things converge. In different types of problems, you would want different types of proposal strategies. So there's the independent proposal, where I just have Q is equal to some independent proposal. But I've kind of told you about when you're searching over a space, there's 2 things you want to do. You want to basically be able to jump around that space freely, but you also want to be able to exploit what you've learned. So if you're in a high mass part of the space, maybe not propose far away from it, and try to refine what you've learned about that part of the space. So I think that makes sense. That's what I call a life principle. We'll talk about life principles when we study Metropolis-Hastings, because I think it can tell you everything about the journey that you're on. So you want to converge to something, and you want to make sure it's good. So that's another thing I like about Metropolis-Hastings, is it teaches me about life philosophy. So great math, great tool, so great algorithm, and great philosophy. So there's nothing more you can get out of this algorithm. I'm going to kind of leave this stuff out. There's random walk proposals, i.e. I can use something normal. So a typical proposal that people will use is the normal random walk, where they just center everything at where you were last time. That's XT. So when you're updating X star, you propose it to get an XT plus 1. You center it where you were last time, and then you look at some ball around that point. So you can do that in high-dimensional spaces as well, and if you knew about covariances or something like that, you could build that into your search directions. So everybody in MCMC has done everything that everybody else has done in the algorithmic world, and they've said, let's steal from them and look at gradients. Maybe that'll help us with our search direction. That's the Hamiltonian MCMC stuff. So if you hear people talking about Hamiltonian stuff, it means they're using gradients for picking their search directions. I want to just say It has the same downsides as every other person out there that uses gradients when they try to search something. It'll help you to climb mountains fast, but it'll trap you at the top of those mountains as fast as possible too. So they could drag you into local parts of the space and not bounce you out of that part of the space too fast enough. So it has good local properties and bad global properties. Now, if you're searching over a local mode and you wanted to do it quick, using the gradient could be useful for you. There's tempering where you augment the distribution. So if you have multimodal distributions, instead of studying a distribution that's really peaky and really flat in some areas, you can raise that to powers that are less than 1 and it'll flatten out that distribution for you. So there's strategies where you can start proposing out of things that look like your target distribution, but they're flatter versions of it. So there's a lot to that idea, and I'm not going to cover that here. So, but just keep it in mind if you're ever studying something that's multimodal and you're like, my local search algorithm doesn't work, well, you need another algorithm out there. And you might need to augment the distribution you're working with. Equi-energy samplers, so they have fast mixing properties. There's mixture samplers where I can use kind of the best of both worlds. So I can use kind of a local proposal sometimes with some probability, I'm calling that pi, and every once in a while I might use an independent proposal. And so that's some distribution as well, and I can think of nothing that searches better, you know, than a Cauchy, because it always has fact tables. So it's kind of a blind search when you do this, so you might want to adapt these ideas.
The mixture sampling reminds me of an epsilon Ruby algorithm where you have some probability of just staying where you are and another probability of
Jumping, so yeah, exactly.
Something random.
I think the ideas are identical to each other. So that's another thing I love about MCMC is it's idea first. You know, why would I jump around? Where would I jump to? And when would I stay at the same place or around the same place? So very similar idea. So all these exploration tools have the same properties. Good ones search, you know, take giant leaps every once in a while and small leaps sometimes. Question is how small should you search when you're searching around some vicinity? Do you want to tippy-toe around the space or do you want to be more ambitious? And it's kind of the Goldilocks thing. It depends on the answer. You can take too big a steps or too small a steps and you want to get these just right. So there's also adaptive methods that try to adapt your proposal and figure out a good proposal for you in the course of collecting samples. And that's another idea, and I bet you guys could write down an algorithm that's just as good as some of the early adaptive algorithms, and they'll fail just as miserably. And then you'll go on your way and figure out better and better ideas, you know, why it failed, and you'll correct those. And there's software packages that do that for you. So BATS is one of those. So if you've ever heard of anybody talk about BATS, it's an adaptive MCMC. Okay. STAN is another thing. It does something like the Hamiltonian stuff, but there's a problem with the Hamiltonian stuff that it will drag you into a part of the space too fast and trap you. So every once in a while you want to give it a random shake. So you can prove all kinds of cool things about that. Okay. That's at least Markov chain, Monte Carlo, just in a nutshell. What I want to do is I want to implement a sampler for you. And then I'm going to write on the chalkboard for a long time and try to tell you what I did. So again, these are just ideas. So we're just getting a picture in our head of what MCMC is supposed to do. And we're ideas heavy and details light right now. And we'll invert that in a moment. Probably next week sometime. So just keep in mind, we don't have class this Friday. So, but we'll be back for all our classes next week, Monday, Wednesday, Friday, and do a review session. So 4 opportunities to learn this stuff next week.
Just a quick question. On the webpage, the homework 3 is due this Friday. When is it actually due?
Yeah, so it's probably in an old lecture, isn't it? So when is it due? What's that? Yeah. So I think we need to push, right? So I think I'm going to say this. Let's turn the homework in on the midterm, October 30th. So there is a downside to that, giving you the feedback that you need. So you'll probably want to take advantage of all the classes next week. I probably want to quiz you as well. and probably come to the review session. So I can give you ample feedback on everything so that we're all prepared for the midterm. And hopefully next week I can give you one more gift. So don't speculate. I'm sure Josiah's already figured it out. So homework due October 30th. This is at the midterm. Don't worry too much. This is just supposed to give you peace of mind. I can also give you feedback all through next week. Okay, let me just tell you what I've done in this piece of code. This won't make entire sense to you yet. What I will explain to you a little later is, and I've already told you, but I haven't fully explained it, this is a type of Metropolis-Hastings sampling. So where the proposal is the full conditional and the acceptance probabilities are 1. So it's just a little bit of algebra. Just keep in mind the joint distribution, the target, and the full conditional distribution are only off by proportionality. And so in that ratio, everything's going to knock each other out in terms of the kernel of the distribution, and all you're going to be left with is normalizing constants that very nicely equate to 1 when you take the ratio of them. This is a type of Metropolis-Hastings sampler. What I can use is that same algorithm that I wrote down before, and I'm going to pretend I don't know how to sample from a normal, and I don't know how to sample from a gamma. So just to slow down the behavior of everything. So what you're supposed to do is monitor convergence, and if we just ran this algorithm the way you're going to do it in your homework, it's going to converge in 2 steps. So by iteration 3, you're already burned it. And so I don't want you to get too hopeful and expect that to happen in practice. So I'm going to use my theory to slow this algorithm down. Usually in practice, I use my theory to speed the algorithm up. But if I can go in one direction, I can go in the other. So this is just merely done for education and illustrative practices. Do not do this at home. I am a trained professional. Okay, here's my algorithm. I'm going to hand it a few things. This is Gibbs' second example. Don't ask me where the first example went. So I don't teach that one anymore. I've got some data that I'm going to input into this, and I'm going to also hand it the truth, how I generated the data so I can compare my answers to the truth. Now I'm going to cheat it first. And I'm going to start my chain. I'm going to initialize it. These are my initializers. I'm going to initialize everything at the truth. That's something you're not allowed to do in practice. So my burn-in period is going to be 1. I'm not going to have to wait for anything. So I'm going to start in the stationary distribution. We hope the truth is in the stationary distribution. And it's going to converge very fast. And later on, I'm going to change this and do this a little bit more practically. So I've got some priors that I've built into everything. So I kind of flip back and forth between phi scale and sigma scale, so watch out for that. I do have this code up online as well, and I make an intentional error in the code. It's almost undetectable, and I'm going to tell you more about that error next week. I see this error made a lot, and so this code does have that error, and I have a comment in there that says the error occurs where it occurs, and I tell you that I would like you to fix that error. So, and that's part of the homework exercise. So, I like to create space for all of my iterations to save time. So, this is one of the first things you learn. If you just start creating a vector and expanding it on the fly, MATLAB's brilliant enough to do that for you without pre-allocating space, but there's a time penalty for that. If you know how memory works, you'll understand exactly why that time penalty occurs. So sometimes you want to create the space in advance, and everything runs a lot faster. I'm going to initialize everything. I'm going to take my first index. MATLAB's first index is at 1. I use 0 over here, so forgive me for making the change right there. Just going to initialize everything. Then I'm going to plot some stuff for you. I'm going to plot the initializers, and then I'm going to run through this for loop right here. So in this for loop, really in spirit, just has a mu update and a phi update. And I've commented a bunch of stuff out so I can tinker around with this code with you next week. But what I'm going to basically do is I'm going to propose mu. And the way I'm going to do it is I'm going to propose mu from a normal distribution. Now this is ridiculous because mu is normally distributed. So if I did this math up front and I figured out which normal distribution this is, I could sample from it directly. I'm going to pretend I didn't do any math. I don't have any insight on anything, which is kind of preposterous because if I didn't know about this, I probably couldn't do this. So, but this again is an idea. So what I'm going to do is I'm going to sample from the wrong normal distribution. The beautiful thing is I'm using the local proposal for this, and I'll tell you more about it, that there's a lot of nice cancellation when you do this. So this is a symmetric proposal for mu. So I'm going to center it at where I was last time, mu in the previous index, and then I'm going to give it some random jitter. So the step size there is the standard deviation of my proposal. That's not going to match my data in any particular way, and it's just going to walk around some little ball, and I can tinker around with that number to show you properties of convergence. So I'm going to use that as a tuning parameter to speed up the code and slow down the code. Then I have some proposal. Right here, I've done everything on a log scale. So instead of taking ratios, I take differences of logs. I'll tell you more about that. I would like the first time I run this code for you to work. So if you don't do this on a log scale and you use products to formulate your likelihood functions, you're going to have numerical problems with like 6 data points. You know, it won't scale very well. And it gets even worse if you start far away from the stationary distribution. We'll talk more about that next week when we discuss practical issues. So this is all just that simple rule where I look at a log thing, I still call it a ratio, but my ratio is really the difference. I'll switch it over to the non-numerically stable thing later, and we'll work in product form and not sum form, not on the log scale, and this will deteriorate rather quickly. I'll tell you about those details, and I do something similar for phi, and I'll tell you about this. So online, this code is there, and I'll tell you about this correction that you need later on. There's a hint on the web page as well. So there's some notes on Gibbs sampling on the web page. I would recommend you download that page. So the stuff by Wilkinson, and read through Darren's blog on this, and he'll give you the correct answer and how to correct this code. Nice thing about this is you won't be able to detect it when I run it here. We'll talk about some issues. And then everything else in my code is plotting. So let me just pick a true mu. So I'll start with true sigma, 2. So phi is what? 1/4. So square first. So this is just sigma, then inverted. So true phi is 1/4. True mu, we'll pick it to be 7. I'll generate some data right now. So I'm going to generate 15 data points for us. Bam. If you want to look at them, there they are. So they were random. Now I'm going to run my code. So I'm going to hand it the data and the truth for plotting purposes, and a little bit of a cheat that I'm going to initialize everything at the truth. So this might be something that you do when you debug your code. Start it at the truth, and if it doesn't converge, go debug it before you move on to something harder. So this is the truth. It's that little dot right there. And so it's at 1/4 in phi space, that's phi, and this is mu, and it's at 7. So that's where I've used the truth. I'm also going to start my chain there. And there it is. So these are my samples. We're going to talk about all these plots. These are the marginal distributions. This is the marginal distribution for mu. I'm just taking the samples from mu space and throwing away the samples from phi space. That gives me the marginal samples for mu. Somebody help me out. How are these distributed? The other one. These are t. So the marginal samples from mu are t distributed. And what's kind of nice is I didn't do any integrations. It kind of automatically did this in this loop. So by passing this phi at every step, I'm ultimately integrating it out. We'll talk more about that, but you get auto integration when you do Markov, when you do Monte Carlo. When you do joint sampling, you can do auto integration by just dropping the column, and it integrates over it, which is kind of cool. So these are the distribution. This is the marginal distribution for phi, this is some gamma distribution. It's one of these that we wrote down. It's this one. I didn't do any math. They're just distributed that way, and it just, lo and behold, if I drew a QQ plot of these samples against this distribution, it would be a perfectly straight line. So that's kind of nice. And I'm going to have you do things like that in the homework, because I already have a little bit.
What's that thing you just mentioned, QQ plots? Is that basically just measuring the histogram versus the real distribution?
Yes, exactly. You plot the quantiles next to each other. So you take your empirical quantiles and you plot them next to your theoretical quantiles. You can plot histograms, quantiles against each other, so you can build quantile plots out of any distributions. You can compare theoretical distributions or empirical distributions to theoretical distributions. Remind me on Monday and I will give you a 5-minute lecture on QQ plots. These are the joint samples. So I connected them with a straight line to kind of show you the path that they take, and we'll come back and look at those paths. But these ones, I've just drawn them as their actual data points. And this is the stationary distribution. And it kind of looks like everything is worked out. Maybe it hasn't filled in this edge yet. Probably needs to spend a little bit more time filling in that part of the space. And so we'll talk about monitoring convergence and whether or not you have enough samples. But what I want to point out, in mu and phi, this is the joint distribution that we were trying to study from the beginning. So that's this thing right here. This is what it looks like. And I kind of like that. It looks triangular to me. So in some fashion. So it tells me that if phi is low, then my uncertainty in mu is big. If phi is big, then my uncertainty in mu at the top is small. That kind of makes sense. So if phi is big, the variance is small. There's this trade-off. So what's the correlation between these two things? It's 0. So if I fit a regression line through this, it'd be a straight line through there. But there is a joint relationship, and it's not measured by something like correlation. So I just want to point that out. So, but there is information that you can exploit there. So doing joint inferences is probably my favorite thing about Bayes, is it gives us the opportunity to do that, and we're not always stuck doing marginal inferences. Let me come back and fill in all the gaps, tell you about this code. We'll spend some time running it, and then I'll write down exactly what I've implemented on the board, how I've used what I presented in the slideshow, and how I coupled it with this. So there's lots of stuff we still need to connect. That's it for now, you guys. Have a great extended weekend, and we'll be back on Monday to fill in all these gaps. If we need more time on this stuff, if you guys are panicking that we don't have enough time to understand all this before the midterm, I can always push some material. But let's just stay on pace right now and modify next week if we need to. Sound good?